Assalamualaikum and greetings. We are from Group 1 and this is the presentation for STSB2012 subject. For the application of chromium oxide and aluminium oxide, our group focuses on solid oxide fuel cell technology, or also known as SOFC. What is SOFCs? SOFCs is a method used for converting chemical energy from fuel into electricity at high temperature ranging from 500 to 1000 degrees Celsius. How does solid oxide fuel cells work? So, SOFCs consist of thin ceramic plate with three main components, which are anode, cathode, and electrolyte. The anode receives fuel, which typically contain hydrogen from hydrocarbon particles. The cathode receives oxygen, and the electrolyte conduct oxygen ion between the two. The oxygen ion will combine with the fuel to produce electricity and heat. The remaining unreacted fuel will be removed from the system in the form of water.
Now, let's move on to the applications of chromium oxide nanoparticles in solid oxide fuel cells. First up, chromium oxide acts as a protective coating for interconnects, where SOFC interconnects requires protection from external environmental factors such as oxidation and corrosion due to the high operating temperatures. Therefore, chromium oxide acts as an effective protective layer. Moving on to the properties and analytical techniques, where when XRD is used, it confirms the phase stability and crystalline structure, which ensures chromium oxide remains stable at high temperatures. Whereas FESEM shows a dense, uniform morphology for defect-free coating application, and XPS confirms the chemical state of chromium 3+ ion, essential for corrosion resistance. And last up is Raman Spectroscopy, where it validates the structural integrity of chromium oxide under oxidative conditions. So the enhancement to SOFC performance protects metallic interconnects from degradation and reduces electrical resistance and improves stack reliability. One of the examples of chromium oxide nanoparticles in SOFCs are chromium-based coatings, where it has been widely adopted to extend the lifespan of ferritic stainless steel interconnects in SOFC stacks. Another application of chromium oxide nanoparticles in solid oxide fuel cells, where chromium oxide used as catalyst for oxygen reduction reaction, which is also known as ORR. So chromium oxide can serve as a catalyst or co-catalyst for the oxygen reduction reaction at the cathode. So the properties and analytical techniques used are XRD, where it confirms the crystalline structure which influences catalytic activity. And also FESEM, which highlights nanoparticle size and high surface area for improved catalytic efficiency. And XPS shows surface oxidation states critical for ORR kinetics, and as well as Raman spectroscopy, which tracks structural stability during catalytic reactions. So the enhancement to SOFC performance improves cathodic reaction rates, reducing energy losses, and also stabilizes the cathode material in harsh operating conditions. So one of the examples of chromium oxide nanoparticles in SOFCs are where chromium-based oxides have been shown to enhance ORR performance in mixed ionic electronic conductor cathodes.
So we will move on to the third application, which is high temperature catalyst for hydrocarbon reforming. Hydrocarbon fuels are commonly used in SOFCs. Chromium oxide acts as a catalyst for reforming reaction, such as methane steam reforming. And for the properties and analytical techniques, in XRD, it will confirm high temperature stability and phase integrity. In FESEM, reveals nanoparticle morphology for optimal catalytic surface area. In XPS, highlights surface redox properties critical for catalytic efficiency. And in Raman spectroscopy, monitors structural changes under high temperature reaction conditions. And then we will move on to enhancement to SOFC performance. The first one is facilitates efficient conversion of hydrocarbon fuels into hydrogen. And the third one will be carbon deposition, which will ensure longer operational life. As for the example, Chromium oxide has been used in anode-supported SOFC system for hydrocarbon-based fuel processing. Moving on to another nanoparticle example, which is aluminum oxide. The first application will be thermal barrier coatings. Aluminum oxide is used as a thermal barrier coating to protect components from high temperature degradation. For the properties and analytical techniques, in XRD confirms the phase aluminum oxide for superior thermal stability. For FESEM, demonstrate uniform coating morphology for effective insulation. For XPS, highlights oxidation resistance and chemical stability. And for Raman Spectroscopy, validates thermal conductivity and structural integrity. As for the enhancement to SOFC performance, the first one will be, it will reduce thermal stress and prevents failure in components. The second one will be enhances overall system durability under cyclic thermal conditions. For the example, aluminum oxide coatings are applied to SOFC metallic interconnects and anode supports to mitigate thermal fatigue.
Okay, for the next application of aluminum oxide nanoparticle SOFC is by using it as a support material for catalysts. Aluminum oxide serves as a support for catalysts such as nickel or ruthenium in anodes. Properties and analytical technique of aluminum oxide can be observed by using first SRD, which is by confirming the crystallinity of Al2O3 and its compatibility with catalysts. Secondly is by using FESEM, by highlighting the porous structure for optimal catalyst dispersion. Third is by using SPF, which is it will identify strong metal support interaction that enhance catalytic performance. And lastly, by using Raman spectroscopy, which is by tracking structural changes during redox reaction. The enhancement to SOFC performance by aluminum oxide is by preventing the catalyst entering at high temperature, and also by increasing the active surface area for fuel oxidation while also improving efficiency. Lastly, the example of usage of aluminum oxide is by nickel and aluminum oxide supported anode are widely used in SOFC, particularly for internal methane reforming. The last application of aluminum oxide nanoparticle SOFC is by using it as electrical insulator in sealing materials. Aluminum oxide used as an electrical insulator in sealing materials to maintain gas tightness and prevent electrical shorting between SOFC layers. The properties and analytical techniques can be observed by using SRD, uh, by confirming the structural stability at high temperature. Secondly, by using FESEM, by revealing the particle morphology for effective integration into sealant. Third is by SPS, which will show surface stability under oxidative condition. And finally is by using Raman spectroscopy, by detecting phonon modes indicative of their electric properties. Aluminum oxide enhancement to SOFC performance is by maintaining the cell integrity, by preventing gas leak, and also by ensuring electrical isolation between layers for efficient operation. Finally is the example. Aluminum oxide-based sealing material have been used in planar SOFC design for improved operational stability. Thank you.